We've all seen it, right? On shampoo bottles in our science class, maybe even when we're trying to figure out our garden. Those two little letters, pH. But what does that really actually mean? Well, today we are going to pull back the curtain and unravel the secrets of the pH scale, all the way down to the molecules that make it all tick. Okay, so let's start with what we already kind of know. The whole idea of acids and bases isn't just for some fancy chemistry lab. Nope, they're in your kitchen, in your bathroom. They are literally all around us all the time. And think about it. We have a gut feeling for this stuff already. We know lemon juice is sour, it's acidic. We know that household bleach is this harsh, powerful cleaner. Well, the pH scale just takes that intuition and slaps a number on it. So that super sour lemon juice, it's sitting down at a pH of about 2. And that bleach, it's way up at a very basic 13.
But this is the real question, isn't it? We've got these numbers, but what are they actually telling us? What is the hidden machinery that's actually at work here? Well, the answer is surprisingly elegant, and it all kicks off with the most common molecule on the entire planet.
And believe it or not, the key to this whole thing is water. The entire concept of pH is built on this really surprising secret that the water molecule has been keeping. You see, it's not just some passive liquid. It's an incredibly active player in this whole chemical story.
So get this, in any glass of water, a tiny fraction of those H2O molecules are constantly breaking apart. They split into a positive hydrogen ion and a negative hydroxide ion. And just as fast as they split, they get back together. It's this continuous, reversible little dance that sets the stage for everything else. Okay, so here's a quick but super important detail. We talk a lot about these free-floating hydrogen ions, this H+, but in reality, these little guys, these protons, are so reactive they never, ever stay alone. The instant one pops off a water molecule, it zips over and latches onto a neighbor, and that forms something called a hydronium ion, or H3O+. And the way these ions move, well, it's just incredible. So how does this positive charge get around in water? It's not some ion just casually drifting through the solution. No way. It's much faster. It's what scientists call a proton hop. It's like a lightning-fast relay race where a proton jumps from one water molecule to the next, like passing a bucket down a line of firefighters. And this bucket brigade is exactly why acid-base reactions in water are some of the fastest reactions known to chemistry. It's wild.
So you've got this constant splitting and reforming, this high-speed proton hopping. I know, it sounds like complete and utter chaos. But underneath all of that action, there is a fundamental, unchanging mathematical rule that's holding it all together.
And this rule has a name, the ion product of water, or Kw for short. And what it says is this: if you take the concentration of hydrogen ions and you multiply it by the concentration of hydroxide ions in any water-based solution, I mean any of them, you will always get the exact same number. It is the bedrock rule that governs all of this. And that constant number is tiny. 1 times 10 to the negative 14th. Now, you don't have to memorize the number. Just get what it means. It creates this perfect seesaw effect, right? If you add an acid, the number of hydrogen ions, the H+, shoots way up. So to keep that final product the same, the number of hydroxide ions, the OH-, has to plummet. It is a perfect balancing act every single time.
Now, let's be honest. Working with numbers like 10 to the minus 7 or 10 to the minus 14 is, well, it's awkward. It's a pain. So to make life a whole lot easier, scientists came up with a much more user-friendly system, all based on this constant.
They called it the pH scale. And all that little p means is take the negative log of. Now, hey, don't let the word logarithm scare you off. It's just a math trick to turn these really awkward numbers with tons of zeros into simple, clean numbers we can actually use. So, in pure water, that H+ concentration is 10 to the negative 7. The pH scale just grabs that little number in the exponent, the 7, and makes it the star of the show. That's why neutral is 7. It's not some random choice, it comes directly from the math of water itself. How cool is that?
And right here, you can see that seesaw in action. Just look. At a pH of 2, you have a ton of H+ ions, right? And that means the OH- concentration is incredibly low. Now jump down to a pH of 10. The whole situation is flipped. It's always a trade-off, with that Kw constant acting as the pivot point in the middle.
Okay, this is the crucial point, so listen up. Because this is a logarithmic scale, it is incredibly powerful. The difference between a pH of 6 and a pH of 5 isn't just one little step. No, it is a 10-fold increase in acidity. So that coffee you're drinking at pH 5,
It's 10 times more acidic than milk at pH 6, and 100 times more acidic than pure water at pH 7. It's a huge difference. All right, so now that we've got the pH scale to describe a solution, let's zoom in and look at the molecules themselves. How do we describe the inherent strength of an acid, separate from whatever solution it happens to be in?
For that, we use a related term, pKa. It uses the exact same negative log trick as pH, but instead of measuring the H+ concentration of a solution, it measures an acid's character. The pKa is a fixed number for every single acid that tells you how much it wants to give away its proton. You can think of it as the acid's personality. A really low pKa means a very generous, very strong acid. So if pKa is this fixed, inherent property of a molecule, how in the world do we actually find out what it is? Well, the answer lies in this classic, really elegant lab procedure called a titration.
So picture this. You've got a beaker of a weak acid, like the acetic acid in vinegar. You start to slowly drip in a strong base, and you're measuring the pH with every single drop. That base is neutralizing the acid, turning it into its partner molecule. But we're looking for one very, very special moment in this whole process, the exact midpoint. And here it is. This is the aha moment, right at that halfway point, where exactly half of the acid has been neutralized. The pH that you measure in that solution is numerically equal to the acid's pKa. It's amazing. By finding this unique point of balance, we can experimentally figure out an acid's fundamental, unchanging strength.
So let's lock this in once and for all. Here's the best way to think about it. pH is like the weather. It describes the conditions of the solution right now, and it can change in an instant. But pKa is like the climate. It's the fundamental, unchanging character of the molecule itself. One describes the moment, the other describes the personality.
Look, this might all seem like abstract chemistry, right? But this incredibly delicate balance is happening inside your body right now, as we speak. It is absolutely, positively fundamental to life itself. That number right there, 7.4, that is the pH of your blood. And your body's number one priority, 24/7, is keeping it right there, within a tiny, tiny fraction of a point. If your blood pH drops below 7.35, it's a condition called acidosis. If it goes above 7.45, it's alkalosis. Both are extremely serious medical conditions.
So why is this so critical? Well, because basically every single enzyme, every protein, every biochemical reaction that is keeping you alive has evolved over millions of years to work perfectly within that tiny pH window. If the pH changes even a little, proteins start to change their shape, enzymes just stop working, and the whole system begins to fail. It is the absolute foundation of our internal stability, what scientists call homeostasis.
And that really leaves us with a final thought, doesn't it? We've just seen how this one invisible rule, the ion product of water, creates a scale where tiny, tiny shifts can have massive consequences for life itself. It's just a powerful reminder that we are built on a foundation of precise, delicate, and often invisible chemical rules that are silently, constantly keeping everything in perfect balance.